In this video, we're going to be discussing a lab activity that we did in class to model the concept of equilibrium. And equilibrium is a really important concept that will be popping up throughout the next several weeks in both Unit 7 and Unit 8. So it's really important to understand fundamentally what equilibrium is and what it means. And to understand equilibrium, we first have to come to terms with the idea that most reactions that we see are reversible. And that means that, typically we've seen reactions represented like this with one-way arrows where we show reactants turning into products, and we think that's that. But it turns out that most reactions in reality are reversible, meaning that reactants are turning into products. At the same time, products are turning back into reactants. And when we look at equations like this, they're reversible. There's arrows going both directions. We still call the thing on the left the reactant and the thing on the right the product. And we refer to this reaction going from reactants to products as the forward reaction. And then we refer to this other direction as being the reverse reaction. And so what we did in this activity is we were modeling out this idea of reversibility, and we have a forward reaction and a reverse reaction occurring simultaneously. And then through modeling that out, we're going to see that these systems, when you have a reversible reaction, these types of reactions will reach equilibrium. And so we're trying to think, what does that mean to reach equilibrium? What is really happening here? And one of our lab skills we're looking at is being able to make graphs. We're going to make a graph on graph paper, thinking about the scale and units and labeling our axes and all that good stuff. So our directions here, which in a moment I'll turn things around so you can see me model this, but what we're doing is we're going to use a volume of water to represent our amount of reactants or products. And so we're going to have two graduated cylinders. One of them is going to have some water in it. One's going to start out empty, and we're going to use straws to transfer liquid from one container to the other to see what happens to our amount of reactants and products over time. And we're going to end up making a graph. So if you haven't done this already, I want you to, before we start doing the reaction, is I want you to, in this area where it says predictions, you want to make a prediction of what you think this graph would look like. Here's an example of some predictions some people made, but I'll erase that. I don't want to influence you. So what we want to do though is we're going to think about what's going to happen to our amount of reactants and products over time in our various experiments. So you're going to read through the procedure, pause, and make a prediction first. Okay, so I'm going to flip my screen around and show you this experiment. All right, so we're going to demonstrate this reaction right here. And so what we have to start with is we have a graduated cylinder mark reactant, and it's got 20 milliliters in it. So this represents 20 moles of reactants perhaps. And then we've got one marked product, and this one is empty. So we're going to start with 20 reactants and no products. And we're going to use straws to represent the reaction that's occurring. And so what I'm going to do is I'm going to use a straw, and I'm going to place it over here in the reactants container. And then I'm going to put my finger over the top. And notice when I do that, if I lift it up, some liquid comes out of my container. Okay, so I'm going to, so this is going to represent my forward reaction, is this one straw over here. I'm going to pick this up and take some liquid, and I'm going to move it over here to the products. So that represents my reactants turning into products. That's what we call the forward reaction. And then I'm going to have a partner who's over here and is representing the reverse reaction. So they're going to turn their products back into reactants. Well, you'll notice is my product has 2 straws. My reactant person only has 1 straw. So we'll think about how that might affect our results here. So we're going to start out with 20 mils of reactants, 0 products. So we're going to take this and we're going to transfer that over. And at the same time, you're going to drop it and let go. And then you're going to get down at eye level, and you're going to record your volumes there of your reactants and products. And then we're going to do it again. So we're going to cover up the straw like this. And at the same time, simultaneously, we are going to transfer the liquid over. So what these are representing is and then you're going to take your volume reading. Okay, so what we're representing here is we're representing the forward and the reverse reaction. So the amount of liquid that's in the straws that represents our reaction rate. It's telling us how much, reactant is turning into product or product turning into reactant over time. And you might notice if you look at the amount of liquid in the straws, initially we had way more moving from the reactant to the product, right? But notice how that's starting to level off over time. So I'm going to keep doing this. I'm going to do this 10 times. Okay. And I'm not really counting, but notice how, again, the volume is starting to become a little bit more similar. And at some point, we will reach the point where the volume of liquid going from reactants to the products is going to be the same as the volume of liquid that's going back from the products to the reactants. And when that happens, we have reached equilibrium. And I think we're about at that point right now, actually, where we've reached equilibrium. Okay. And notice that when you reach equilibrium, I don't know how well you can see these two containers, is that notice how at equilibrium, the amount of reactants, the amount of products is not the same. I might need to hold it up like this. Okay. So it looks like we have about, we should end up with about maybe like 13 reactants to about 7 products. So we didn't end up with an even split. We didn't have like 10 of each. So equilibrium does not mean that the amount of reactants is the same as the amount of products. What it means is that the amount of liquid going this direction is the same as the amount of liquid going this direction. So what that means in terms of the chemistry, that means the rate of this reaction is the same as the rate of that reaction. So we've reached equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. And I'm going to pause again in a moment, and I will post some sample data that you can look at to make a graph if you missed doing this in class. Here is a sample set of data and some things that you will want to, and you want to use this data to make a graph if you missed class on the day we did this. Otherwise, you should use your own data. And some things that we should notice is that in all these cases, we've reached equilibrium. But when we reach equilibrium, notice how the amount of reactants and products is not the same. What does happen at equilibrium is that the amounts of reactants and products stop changing. And that's because the rate of going from reactants to products starts to even out with the rate going from products back to reactants. And that's why we say that this equilibrium is dynamic, is because all the liquids keep moving. They keep going. It's just they're going from here to here at the same rate as they're going from here back to here. So that's important to understand about equilibrium. Is it doesn't stop. It just keeps moving just the same rate forward as backwards. So that happens in both cases. And notice how it doesn't matter whether you start with 20 mils reactants or 20 mils products, we still reach about the same equilibrium position. So at equilibrium, you have more reactants than products. It's about a 13-7 or like a 12-8 ratio roughly. If our data was perfect, we'd end up with exactly the same ratio each time. But this is real numbers, so it's not exactly perfect. But that's what we're seeing here. So it doesn't matter what you start with, you will reach the same point of equilibrium. And that's going to be dependent on the reaction. So for this reaction, we end up with more reactants than products at equilibrium. For some other reactions, we might end up with more products than reactants. And so we will talk more later in class about how to find things like the equilibrium constant and all that good stuff. But for right now, what you want to do is to be able to make a graph and just think about what it means to reach equilibrium.